Completing prices and drilling investment. Let us go back to the price issue in order to complete this part of the model. 56. On cell H8, write the following formula, equals average prices. C14:C396. This formula yields a value of 4.65%. This is the average annual variation of prices according to history for WTI for the 33-year range between 1986 and 2018. This cell has been previously named as price var. We will later use this calculated parameter for creating price-time dependency onto the model. 57. On cell B15, write the following function making reference to the three parameters required by a PERT distribution for price. Equals risk PERT, open parenthesis, min price, comma, ML price, comma, max price, close parenthesis. These parameters have already been named and are located on range B5:D5. It could be reasoned here that each one of the prices for the next 19 years could also be modeled with the same PERT function. Copying and pasting this function for the remaining range would, however, not consider time dependency. Even though the PERT function by itself captures the inherent variability of price, it does not consider time dependency. Unless we add a method to consider that a price for the following year somehow depends on the past year's price, this method would be a poor one. There are many ways in which time dependency can be added to this model. As a matter of fact, at the end of this module we will incorporate time series tool in at risk, which allows for that as an enhancement to the model. At this point, so far, we will add time dependency with a simpler method. 58. On cell C15, write the following formula, equals B15 times risk normal, open parenthesis, 1, comma, price var, close parenthesis. Remember, price var makes a reference to the average historic price variations on WTI price for close to 33 years. This stochastic formula applies a normal variation to an initial price on year 1 for which a PERT distribution has been defined. 59. Copy this cell and paste it for the range C15:U15. 60. On cell V15, insert the following summarizing formula to record the average price for the 20-year horizon, average B15:U15. We will now insert capex for drilling wells starting on cell B16. If we were to multiply the number of drilled wells at each year, 5 or more, times a single simulated and stochastic value of capital expenditure per well, we would be doing a naive simplification of the model, assuming all wells would cost the same at every single iteration of the simulation. This is not necessarily true, unless the drilling contractor has agreed to charge exactly the same amount per well regardless of drilling conditions. For example, if 7 wells are to be drilled at any given year, each one of them assumes a different Weibull-generated value for its capex. If you were to multiply, at each iteration, 7 wells times an iterated amount, we would be assuming a rigid amount at this level. The good news is that in order to create the correct convoluted or compounded distribution, we do not need to create a one-by-one case for each drilled well times its capex amount. At risk does have a very powerful function that does all of it, the convolution, automatically. It is called the risk compound function. It is used to return the sum of a random number of independent random values from a specified distribution. Specifically, it returns the sum of a number of samples from the second distribution, where the number of samples drawn from it is given by the value sampled from the first distribution. Typically, the first distribution is called the frequency distribution, the negative binomial, and the second distribution is the called severity distribution. 61. On cell B16, type the following function. Equals risk compound, open parenthesis, B12, comma, risk Weibull, open parenthesis, drill param 1, comma, drill param 2, close 2 parentheses, times 1000. 62. Click on the define distribution icon of at risks ribbon. You will see the following compound function. The B12 value on the frequency parameter represents how many wells have to be drilled. This variable is being driven by the negative binomial function plus 5. If you click on the Weibull part of this function on top of the cell formula dialog, you will be able to see the severity or capex part of the individual investment per well. Risk compound is evaluated each iteration of a simulation. The first argument's value is calculated using a sample from the frequency distribution. Then this number of samples are drawn from the impact distribution and summed. This sum is the return value for the risk compound function. In other words, use the compound distribution to automatically multiply frequency or number of wells, which in turn, depends on a negative binomial function times the capex amount, or impact, with a fitted Weibull distribution. 63. Exit with OK and copy and paste this function to the range B16:F16 for each one of the 5 investment years. 64. On cell V16, write the following formula to summarize the total nominal capex amount on drilling wells, sum B16:U16.